Well, good afternoon, everyone. I have some work from 11.3, Powers of Complex Numbers today. Oh, I see a stray mark. Anna Gatherum's going to kill me, so I better get rid of that. So let's jump right into it. At this point, I'm assuming that you've all read 11-3 and worked the examples. I have an example that's not in the book today, so this should be fun. So let's say that you have square root of 3 minus I, complex number in the form a plus bi. In this case, b is just 1, but that's okay. And let's say you're feeling especially mean and you want to raise that to the 4th power. Okay? Obviously, we can jump right into that and do it with good old-fashioned heavy lifting. To start with, though, let's go square root of 3 minus I squared, I think is a little better way to approach this, which would give us the square root of 3 minus I times, of course, quantity square root of 3 minus I. So far, so good. And then let's go ahead and FOIL that out. Square root of 3 times square root of 3 is just 3 minus the square root of 3I minus square root of 3I plus I squared. And if we clean that up, we get 3 minus 2 square root of 3I. And I squared, of course, is just 1, negative 1 rather. And so one final step we can say then that is 2 minus 2 square roots of 3I. Okay, and remember that equals the square root of 3 minus I squared. So then we can just take this and square it to get our square root of 3 minus I to the 4th, then would equal square root of 3 minus, don't need that yet, minus I squared times square root of 3 minus I squared. And now we can just substitute in this part right here in for that. And that should be kind of nice. So now we can say equals 2 minus 2 times the square root of 3I squared times itself minus 2 times 2 minus 2 times square root of 3I. So once again, we can FOIL that, and it'll work out okay. So then we get equals 4 minus 4 square root of 3I minus 4 square root of 3I plus, this one's a little bit trickier, so let's go slow here. 2 times 2 is 4, negative 2. Square root of 3 times the square root of 3 is just 3. And then I times I is I squared. So you might want to stop and back that up and work it slowly. This gives us then 4 minus 8 times the square root of 3I plus, oh wait, I see I goofed up here. You guys, I think I said it right, but wrote it down wrong. Up here, square root of 3 times the square root of 3 is just 3. Don't do that. Eek. Sorry about that. Everything else is right. So then 4 times 3 is 12. So plus 12. And of course, I squared is negative 1. 12 times negative 1. So when we put all that together, we get negative 8 minus 8 times the square root of 3 times I. Okay? How cool is that? I like it. I like it. Now, You know how I love to do the beautiful thing in math, and that is compute the same thing by two different methods, computing the same thing by two different methods. So let's just bring this down. I'm going to group these guys. Grouping, group. I am going to clone and bring this on down. A little more, a little more, a little more. Okay, let's say we want to do this same thing by a little different method, and we'll go green. Okay, so now in your book, you saw De Moivre's theorem, and De Moivre was a smart guy from France, of course, who got picked upon because of his religion and moved to England. He lived back, I don't know, like 1670 to 1750, somewhere in there, lived for a long time, did lots of math, became a pal of Sir Isaac Newton after he moved to England, did a lot of work with probability, a lot of work with complex numbers, and was credited with linking complex numbers to trigonometry, which is exactly what we're doing here in section 11.3. So, very cool. Let's say we want to use De Moivre's theorem and try to compute and come up with the same answer for square root of 3 minus I, quantity to the fourth power. Try to come up with negative 8 minus 8 times square root of 3 times I. So let's jump into this. We got to do a little bit of work first, though, to set this up, because this is in a rectangular form, and we need to get it into polar form. Okay? So let's, as always, draw a little picture, because we love pictures. And so we would have our real axis here, and our imaginary axis here. And on the real axis, in this corner, we have the square root of 3. And here, remember, this is negative 1, a plus bi. So this is negative 1i. I need this. I'm going to extend this just a little bit. So yeah, this is negative 1. And so that's what we're looking at here. Something like this. So here's our negative 1. Here's our theta. And let's figure out what this cat looks like. So using Pythagorean's theorem, of course, we can say r squared, and r will be here, r squared equals the square root of 3 squared plus negative 1 squared. And remember, your calculator will lie to you if you don't use parentheses. But you can probably do this one in your head. R squared equals then 3 plus 1, and r squared equals 4, and r equals 2. Okay, so that's the first part. R equals 2. And then we need to consider what theta equals. And looking at our diagram here, from theta, this is negative 1 is opposite, and this is adjacent. You can use 2 as well, but since we started with these two, I'll stick with these two. Opposite and adjacent. Sure could tell. Oscar had a heap of apples. Opposite and adjacent would be tangent. Tangent. And we have negative 1 and 3. Okay, so I can say the tangent of theta equals opposite negative 1 over the adjacent square root of 3. So theta equals the arctan of negative 1 over the square root of 3. So theta equals negative 30 degrees. And that makes sense. That makes total sense. So theta equals negative 30 degrees. So our rectangular coordinates are negative 3 minus 1i. And our polar coordinates then would be r, which is 2, and theta, which is negative 30 degrees. Now, that's great, but we have to consider, because this is a negative 1i, not just a negative 1, we have to put in here our, oh, they're stuck together. I'm going to have to write it again. What a bummer. We have to consider, because it's an imaginary number and a complex number, that this is in polar form 2 cis negative 30 degrees. And then the whole thing we're going to take to the fourth power using de Moivre's theorem. Okay, so this will work. And our theorem from your book on page 408 is z equals r cis theta and z to the fourth equals 4. Well, I should do it in general terms. That's not right. That's messed up. I should do it in general terms. So z equals r cis theta. So z to the n equals r to the n cis n theta. Okay? So we'll do that. And so now you can see we have here, let's plug it in, 2 cis negative 30 to the fourth, whole thing to the fourth, equals 2 to the fourth cis 4 times negative 30 degrees. Okay? 2 to the fourth, of course, is just 16 cis. 4 times negative 30 is negative 120 degrees. And then we better write that out. I think now is a good time to remind ourselves what that cis is. We're probably not totally comfortable with that yet, I'm guessing. So this equals 16 times the quantity cosine of negative 120. There's the c part in cis. Plus I, imaginary number, times the sine part of negative 120 degrees. And 16, note, is outside, so we have to distribute that throughout at some point. Okay? So then we go equals 16, and you can use your unit circle or whatever to acquire. At this point, hopefully you've memorized the cosine of negative 120 is negative 1/2 plus I times, same thing, sine of negative 120 is square root of 3 over 2. In this case, because negative 120 is in quadrant 3, we would say the negative square root of 3 over 2. Quadrant 3, they're both negative. Okay? And I'm going to use parentheses just because I like to. Okay. Cool. And then we have one more step, equals negative 8 minus 8 times the square root of 3i. Guess what, ladies and gents? That is the same thing that we got up here. Negative 8 minus 8 times the square root of 3i. Negative 8 minus 8 times the square root of 3i. Being able to do things in two different ways makes you that much more powerful mathematically. So, hope you enjoyed this and it was helpful. If you have more questions, please feel free to ask in math class tomorrow. That is all. Have a good one.